Hello and welcome. In this video, we will learn how to do numerical integral with Simpson composite rule. And in this video, we will learn how to do double integral right now. So the first double integral we want to solve or we want to apply here is the rectangular region. The rectangular region means the lower and upper bound of the integral is a constant. So A, B, C, and D must be a constant number. So this is the general form of the double integral with rectangular region. And how do we find the solution? Is the first step is to integrate the within the square bracket here the function f(x,y) with respect to y. So the result of the integral can be seen here. It's similar to the composite Simpson's rule as we have talked before. And remember, in this integral we still use hy, which is a constant value because we use a rectangular region here. And the y itself is c plus j multiplied with hy here. The j start from 0 to 2 multiplied with ny. Ny is the number of division on y-axis. So we simplify the formula. We simplify the expression here, so we get this. And the next step is to integrate the whole part here with respect to x. As you can see, we have this function in the bracket here to integrate with respect to x. And because we have a lot of terms here, we can do some simplification here. For example, here we introduce a variable int, means integral 1g. The integral 1g is equal to the integral from a to b fx yg dx. In this case, we have this result. We have a similar result actually, but this time we integrate with respect to x-axis, so the x will play as a main part here. So after that, we also define the step size here and the x as well. The x is, remember, it is a plus I multiplied with x, hx, and I is start from 0 to nx. Nx is the number of the subdivision on x-axis. So by doing this simplification, we have a final result here of the double integral with rectangular region. So we have 2hy divided by 3 multiplied with this part. And remember, on each term here we have this, right? So basically, as you can see, the double integral is basically the summation of the single integral here. So we sum the result of the single integral from g equals to 0 up to g equals to 2n here. And in this example, we want to solve this one. We will apply this mechanism into the code. And how do we do that? Well, we can go to the code here. Here we have the code of the double integral using the composite Simpson's rule and with a rectangular region. And in this program we have variables and parameters. A is the lower bound of the integral as we have in this expression. A is the lower bound of the integral on x-axis, and B is the upper bound of the integral on x. And also C and D. C is the lower bound of the integral of the y-axis, and D is the upper bound on y-axis. And we use y here. We also use y. What is y here? Y is used to calculate the integral one, because the integral one is a function of y, I think here. As you can see, the integral one is a function of g. It means it depends on y, right? So because y depend on g, and so that's why integral one here depend on y. Okay, we can have a look to the final expression of the result actually here. The first line here, this subroutine, I mean this line calling the integral one subroutine, it computes this part. As you can see, the y equals to c means the y0, or the g equals to 0. So we get this, and we store the result into the integral variables, and then the last y, I mean the y where g equals to ny. Sorry, I have something to ny. And this line, this calculation is performed here by this line, and we store the result into the integral variable again. And the next is this line. This line, as you can see, we calculate this part. We actually use the similar expression. As you can see, we start from 1 until 2 and y minus 1 with the step size of 2 here. Okay, and on each iteration we introduce the y as a function of g, because in integral one it depends on y here. Well, actually we can use integral one as a function of g, but it's just a matter of style. You know, you can modify the code later. And we store the result into the integral variables here. And the last is calculating this last term. Integral 1 to g minus 2 from g equals to 2 to ny, or from g equals to 2 to 2 multiplied with ny minus 2 with the step size of 2. Okay, the interesting point is we need to have a look to the integral subroutine, the integral 1 subroutine here. This is basically it's similar to the first integral we have, the first integral code we have with Simpson's composite, but we transform we modify the code to become subroutine, so we can call it multiple times in our code. So as you can see, it's similar to this line maybe. Integral 1 as a function of g, or integral 1 as a function of y here. So we calculate the fxo where the x equals to a, right? Xo equals to a, and x to n, oh sorry, this is 2 and x, it's supposed to be x. Okay, the nx, fx to nx is basically c, the upper bound of the x-axis. So this line calculate these two terms, and the next is calculating this term as we have before in Simpson's composite rule in one-dimensional integral. And also the last part here, we calculate this term. So basically, as we learn the double integral numerically, we know that the double integral is basically the summation of single integral. I mean, the summation of integral in one dimension. So that's all, I think, for this integral with double integral with rectangular region. And in the next video, we will learn how to modify this code to solve double integrals numerically. So see you soon. Bye.